Hi, I'm Lyndon White. I'm here to talk to you about the ChainRules.jl project, a agnostic custom rule system for the Julia language. Shown up on screen are some of the many collaborators on this project. So let's get started. So what is the ChainRules project? I mentioned before, it's an extensible AD agnostic set of AD rules and a system for defining them. It is made up of three key packages: ChainRules.jl, the system for defining rules; ChainRules.jl, all the rules for the Julia standard library; and ChainRules test utils, a robust system for testing the rule definitions, as well as several other auxiliary packages that I won't go into today. Why do we need this? So AD primitive rules have three key uses. Fundamentally, we need them for the basic primitives of the language itself, which at very least is addition, but probably is a bunch of other operations, since anything that's been defined, not in terms of, well, a more primitive operation needs a rule, which tends to often include things that were defined in like another programming language, since most AD systems can't AD through calls into other languages. But secondly, we need it for adding domain knowledge into the system. So using various pieces of domain knowledge, we can make differentiation possible where it wouldn't otherwise be, or much faster. This is things like the implicit function theorem, or the extensive amount of work that's gone into local sensitivity analysis methods for differential equations. Finally, we need it to work around imperfections in the AD engines. So ideally, the AD engine would be able to handle all code, and it would generate the most optimal code possible. In practice, this doesn't always happen, and so by using custom rules, we can solve this. Well, work around it at least. To explain how this hangs together, I mentioned those three packages before. So here's how they get used. ChainRules core, which defines the system for defining rules, gets loaded up by packages like specialfunctions.jl or nnlib.jl, and they use it for defining how to take derivatives through the functions they've defined. It is used similarly by ChainRules.jl, which is used to define how to take derivatives through the Julia standard library functions. Then over on the other side, we can see how it's used by overloading ADs like Nebula and source-to-source ADs like Zygote. So these ADs depend on ChainRules core, so they have access to that API. And ChainRules.jl, since they need access to, at very least, the rules for the standard library. Something you can note here is that Zygote never depends on nnlib, nor the reverse. Instead, they both depend on the common ChainRules core library. This means that when, say, Flux, a user-facing neural network package, loads up both Zygote and nnlib, Zygote can take derivatives through the nnlib functions, but there's no direct dependency between them. So we released version 1.0 of the ChainRules project at JuliaCon this year in August. Right now, ChainRules core is used to provide rules for about 70 packages, which downstream of them is something close to 2,000 packages. And it's supported by 6 AD engines. I've put them up on the screen now. You can see they are pretty varied. So I think it's working quite well right now. So I'm going to spend the first part of this talk talking about the key requirements we had to solve in this project. So I've got them up on screen now. We have 6 key requirements. So first, we want to be mathematically sensible. This means we want our tangent objects to be reversed by types, which can be added to the primal, and they basically define vector spaces. I'll talk about these more in a bit. We don't allow real numbers to have complex tangents / cotangents. We don't allow diagonal matrices to have dense tangents. We don't go around pretending that booleans or integers represent continuous quantities. No such thing as like false 0.1. You can't perturb a boolean or an integer. We distinguish between something not being implemented versus it being 0 because it's not part of the computation, versus there being no tangent space at all. For example, when indexing, there is no tangent to the index operator. You cannot look at something that is the next bit further along. They only go up in a discrete quantity. There is no tangent space to indexing. If you're familiar with Zygote, these are basically lessons learned from Zygote. Zygote is not mathematically sensible, at least not in the parts that don't use ChainRules.jl. So this is something that we took care to try to do better at. So I mentioned this before. Technically, all we actually need for our tangent type is to add two other tangent types, since that allows us to do gradient accumulation, etc. But practically, we'd like it to have everything you'd expect from a vector space. Having more linear operators makes it much easier to define the rules. And we also define addition from the tangent to the primal value to get back another primal value, which allows it to be used directly for optimization and also resolves dispute as if two representations are equal, since no matter how they're represented, if you add them to the primal value and end up in the same place, they must be equal. Another requirement is that it's extensible. So the predecessor to the ChainRules project was the diff rules project. And it had a number of limitations, and one of them was that it wasn't extensible. So diff rules defined rules inside the diff rules package for base, the standard libraries, and one or two packages like special functions.jl. Then packages like Nabla or Zygote loaded up diff rules, and they had access to those rules, but only those rules. You couldn't add any after the fact. So if some package did want to add rules, like this foo.jl, then it would either, foo.jl would have to depend on, say, Nabla, and would implement some things as accessing Nabla's internals to add rules to it. But that wouldn't be great, since then those rules couldn't be used by Zygote. Or the other way around, Nabla would depend on foo.jl, and it would, well, basically would access enough knowledge about how that package worked in order to define a rule for using it. Again, this would be not useful to Zygote or other AD systems, and it would also be potentially quite fragile if the foo.jl package changed. So ChainRules.jl carefully overcomes this. We make sure that you can add rules after the fact, and you don't have to depend on your AD system directly. We require that the rule system can represent anything that any AD can handle. So most AD systems, I think all, can handle scalars. Most can handle matrices. But some can also represent structures and tuples. So we need to be able to represent structures and tuples. We need to be able to represent derivatives through callable objects. So things like functions and closures, where the function itself has some field or state. Yeah, our rules need to represent that as well, not just simple functions. It's required that you're able to call back into the AD system. So if writing rules for a higher order function like map or reduce, then inside that rule, we need to be able to do AD on the thing that we're mapping over. And we can't just hard code to use a particular AD system, since our rules need to be AD agnostic. And furthermore, we may want to expose different rules depending on the capabilities that the AD system has available. So Diffractor, for example, is an AD system that supports both reverse and forwards mode. The most efficient way to compute the AD through map in reverse mode is actually to use forward mode on each element. So we have a configuration system where the AD engine specifies which features it supports, and then different rules are enabled for it to use. We require that you can share work between the primal or forward pass and the pullback or push forward. So in reverse mode, consider we were doing AD through the computation of eigenvalues. We want to change the primal computation to compute eigenvalues and eigenvectors, which can be done efficiently together, because we need those eigenvectors in order to be able to compute the derivative. And so we need to, well, yeah, remember them for the reverse pass. Similarly, in forward mode, we'd like to be able to compute the primal result and the tangent as a single operation. So we fully fuse the push forward and the primal computation together. This lets us do things like express the, use local sensitivity analysis methods from differential equations in order to use a extended differential equation that will give us our both single operation, which we can then pass entirely to the differential equation solver, which will, solve it in a single hit. Finally, we require that the package is minimally magic. So the whole thing works basically just by overloading functions, which in Julia is how you extend most things. There's no fancy macro-based DSL you have to learn. We consistently always represent the tangent for the function of itself. We don't change the number of outputs you have to return depending on whether or not that's a functor or not. Our keyword arguments are just keyword arguments. They're not the special internal representation that Julia uses for keyword arguments. All this kind of thing. We want it, as far as the rule author is concerned at least, to be not magic. It's okay if we make the AD author do something clever, and we've helped several AD authors do so. But as far as the rule author is concerned, everything should just work and should be just kind of normal code. We took this priority because there are, as we discussed, 70 different packages using this as a rule author and 6 AD engines. We expect the AD engine author to have more time to deal with intricacies rather than push it onto the people writing rules. I want to spend the second half of this talk talking about the biggest challenge that we've run into, which is polymorphism. So polymorphism is commonly considered one of the 3 key pillars of object orientation. One way to think about it is the ability to provide a common interface over multiple different implementations. For example, consider a diagonal matrix. It could be implemented as just a vector that just holds the elements on the diagonal, but then it could be exposed as if it was a square matrix, so that getIndex was overloaded to be able to read off diagonal elements and just return 0. So it acts just like a square matrix. This is being polymorphic. But furthermore, it can have an efficient implementation of, say, matrix multiplication as column-wise scaling, rather than having to use the triple loop algorithm. So polymorphism seems a natural fit to go with linear algebra code. BLAS, for example, has dense, symmetric, triangular, Hermitian, banded, and triangular banded matrices, plus transposed and conjugate transposed variants of those, each of which is exposed with a different function. But we don't generally see this in typed libraries at the moment. NumPy exposes 3 matrix types. Eigen exposes a different 3 matrix types. Blaze gets a lot closer to BLAS. It has 9 matrix types, and they're quite similar to the BLAS ones. Julia, on the other hand, Julia has 29 matrix types in the standard library alone, plus innumerable libraries that define more, like Woodbury matrices and banded block banded matrices and piles of them. So Julia runs into polymorphism a lot. And it turns out once you have polymorphism going on, you have a whole world of new problems for AD rules. Should rules be written for functions that accept abstract types? And should those rules accept abstract types? We have to worry about escaping the manifold. A sparse matrix must not have a dense derivative. I mentioned this before. And we need to worry about how to convert between the structural representation, considering the matrix as the structure that represents it, and the natural representation where we consider it as being a matrix. As far as I've been able to find out, and I'm happy to hear I'm wrong, there's not much work on this already done. And I expect that this is going to be a problem that more people run into as we start using more polymorphism in real world scientific code. So first of these problems, should we write rules that accept abstract types? In general, in Julia, functions written, they're very generic. For example, matrix multiplication can be implemented with just a triple loop, so it only requires getIndex to be defined. And then specialized overloads are added when domain knowledge is useful. Like if one of the matrices is diagonal, we can replace it with the column-wise scaling, much more efficient. And so you might think that we should do that for AD as well, write some very general rules. However, for AD, there's a counter argument. There's always a very specific, very specialized fallback available to us, which is to run AD and not use a rule at all. However, sometimes when you just run AD, you generate something that's much slower than an abstract rule you could have written, because the domain knowledge you'd use on that abstract rule is actually useful. But conversely, sometimes the abstract rule is much slower than doing AD work, because AD is leveraging all the specialized information that is available to it because it's hitting a specialized primal function. And these can both happen together for the same function. Different methods may be better or worse to actually use it, which put us in a bind. Our current resolution to this has been that we do allow abstractly typed rules, but we make it very easy to opt out of them on a case-by-case basis. The second problem is what I call escaping the manifold. So let's consider a rule for the sum operation. So we're computing the pullback, and what we should end up with is a matrix the same size as our primal, and the value of the cotangent that's being pulled back should be in every element. However, if we just do this naively and we use the fill function, we'll get back a dense matrix. But if the input that we were summing was a diagonal matrix, then that would be incorrect, since that would give us a non-zero diagonal tangent, which is not the case. So you know it can't be, because diagonal matrices don't even have an element there. It can't have possibly been perturbed. There's no space there. So that's a problem. You can do something very similar with real numbers. So if your primal is real, you can end up with a complex cotangent. And to resolve this, we've introduced what we call the projectile operation. It's defined using the primal value in the forward pass. It remembers just enough about anything about the primal value that we can drag back down any tangent types to the manifold where the primal lives. So this means we can drop the off diagonals on a diagonal matrix, and we can enforce symmetry on a symmetric matrix. Furthermore, we can use this to fix the precision of floating point types. So we can get make sure we get only a 32-bit gradient for a 64-bit rather than a 64-bit gradient, if the primal was 32-bit. And we can also use this to reattach name dimensions, so name tensor types and similar, assert correctness and that kind of thing. The last problem I want to talk about is this natural to structural tangent conversion. So we can represent a structured matrix using like a polymorphic thing is a class or a struct. So it has a representation as a struct where it's got fields, and its tangent would therefore be a tangent, a structural tangent with a tangent for each field. But it's also matrix-like, where it is a matrix, it acts like a matrix. We can do the algebra on it. For constructors, we really want to consider the tangent represented like a struct, because we want to attribute the tangents for each field back to the initializers that we use to construct those fields. But for most mathematical operations, we really want it represented like a matrix so that we can run the algebra on it. Now, there's a trivial case here. If the natural tangent has the same type as the primal, then we know all the fields and we can just look them back up and see that they match. But this is not always the case. For example, if our primal was a symmetric matrix, we might get a tangent which is a diagonal matrix, since well, every diagonal matrix is indeed symmetric, and some operations do only have apply on the diagonal. And this is harder. So we're currently working on this, and you can see the link at the bottom for pull request number 449. We believe the correct answer is to use the pullback of the collect or densify operation to do this conversion. Since this operation only requires get index and it accesses each position, mapping it to how do you actually get the value there, which is looking up the fields. Right now, we're proposing writing rules for all of these, but we think something more general can be done using, say, abstract interpretation techniques. So this brings us to the end. To wrap things up, the ChainRules project is an AD agnostic custom rules system for the Julia language. It's now fairly widely used. We took some care to get the abstractions right. And polymorphism, it makes things hard. Thank you.